I think in my profile earlier. So during my study, when I was at Northeastern University in Boston, Massachusetts, I was there for 2 years for my master. But then after that, I had 1 year internship at the solar. It's a research R&D company. So it's a research and development for solar photovoltaic. So I had 1 year internship there. Um, it's called Fraunhofer. I don't think it's in the it's Fraunhofer. It's a Germany company, but it was based in Boston, Massachusetts. So that's how I got. And then my master's school was also like in renewable energy, but it was deeper for solar photovoltaic at that time. After my
Recording in progress.
okay, after my internship. So that's how the very first my 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 how do you call that, my involvement, I would say, my involvement with renewable energy in general. When I got back, when I finished my study and then my internship from 2012 to 2015, I got located from West Sumatra, from Padang to Jakarta. When I was in Jakarta, I was at the renewable energy department. So at least, I'm not sure right now, but at least like at that time, renewable energy department was only at the headquarters. There was no renewable energy in other area. For example, like in Makassar, in the distribution office, there are, at that time there was no the renewable energy. So I'm not sure right now how the department over there. But yeah, that's how I got experience. And then over the time, after PLN, after I left PLN and then coming here, I kept on like working on with the renewable energy. And then also like up to this point, like especially now at PJM, if I'm trying to compare PJM with the PLN, so the differences between um the electric company, I would say, in Indonesia and here in the US, just as a background, is that like in Indonesia, it's like government owned. So PLN is a government owned, right? It's all regulated by the government, and then everything is just like from the head office all the way down. But in the US, it's all private company. And then this private company, they are kind of like based on location wise. So for example, like if you're familiar with US, there's like East Coast, and then there's West Coast. And like East Coast is kind of like from Boston, Massachusetts. So like from Massachusetts all the way to New York, and then New Jersey, and then go down to Pennsylvania, and then go down the south is like Florida. That's like east, right? So that's kind of like the east. And then west is like California. You must be and Seattle for like Amazon office there. They are all in California. So that's like west. So the way PJM PJM covers it's like kalau di PLN itu dia kayak pengatur beban. Kayak misalkan kantornya itu yang ada di Petarani, tapi bukan yang kantor distribusi, dia PL apa gitu ya. Pengatur beban pokoknya. Nah, PJM is just like that. It's like the load dispatch. So like the kind of like those load dispatch is we for PJM we cover like 13 states or 13 provinces in the US, right? So like those are like it all from New Jersey all the way to Illinois, Chicago, all the way down to North Carolina, and then Virginia. So there are 13 states in total that PJM kind of like regulates the electric power grid of that. So based on that, we have all the interconnection. So it's all interconnected power grid, interconnected systems. And then when any generator, right, wants to connect like solar or like wind energy, if they want to connect, we have to do the interconnection study. So that's something that kind of like we will touch in the presentation as well. Touch a little bit why there's kind of like interconnection study. What's the point of that for any project, any generator project? So that's kind of like where I am at right now at PJM as an interconnection engineer. I do the study for all projects that would like to connect into the grid, into the PJM grid. So that's just kind of like the background idea of like, what's the correlation of all of these. So that's for just as a background, the idea of how PJM or like US does the project or any renewable projects in general. So that's the way my interpretation. So how I see energy conversion is not just on the, I said earlier, it's not just at the cell level. Like we have this, for example, like this one. It's not just on this level. It's deeper than that. The way my experience that once the energy converted from sun into the electron, and then it goes into the system itself, it doesn't stop into the project itself. How we deliver all that to the grid, and how from the grid it's consumed, it's delivered to the customer. That's how my experience, my whole work experience, that's how all, when it gets to the customer, that's all the part of the conversion. So my material today here, if you could see here, is the first is just like, the basic. Most of the basic already was delivered by my coworker I had, but this is just kind of like a little bit touch base on this, not too detailed. And then so the solar photovoltaic itself, right? This is just a brief touch base on that, on what had been delivered by my coworker I had. And then the second part of it is the from the solar itself, and then the science behind from the solar photovoltaic becoming why, the science of how this solar energy, what variables really take into account to that, the production, the energy production of it. And then the last part of it, because I've been all my work experience heavily on the project based. So I this is where I'm going to, the part 3 is where kind of like touch base on how to design the project itself, the solar PV project itself, to become, you know, to be delivered to the customer, right? So then that's like large scale. So when I say large scale, in the industry, so in the industry of in the whole industry, is like there is solar rooftop. We in Ahat's presentation, we there was question about solar rooftop, right, which is like it's on the house level, individual house level. But then there's, if it goes to the grid, to the power grid, the bigger, that's what it's called large scale, right? So that's what I would like to touch base on that a little bit. And then the how the design itself, I will kind of like give a little bit idea on how the process of designing this power system for like solar PV, using like it's a simulation software. Yeah, and this is, I'm not really sure whether, I think in Indonesia we have used this. I'm not sure how common it is. Using like, it's, for example, it's called like PVCs. We the one that I have used a lot in the past when I was doing my study and when I was doing my internship was doing using PVCs. So I will touch base on that to introduce how the design of the solar PV itself done. So I'm gonna
Sorry for
pause.
interrupting. Sorry for interrupting. Your voice, it's kind of unstable because I don't know, maybe your microphone.
Can you hear me?
We can hear you, but not too clear.
Think not too clear. Okay, I'm
Okay.
sorry about
Okay,
that.
it's clear now.
I'm
Clear
gonna
now.
have to move my location then. I'm gonna
No,
move.
it's clear now. It's clear now.
Yeah, I'm gonna. It's clear now. Okay, it does say that unstable locate unstable. Not sure. Sorry, I live by the woods. So
I think you need
can
to
you
find
hear
a
me
spot because
better? Much better.
no. It's still unstable.
Okay, give me 1 second. I'm gonna have to go downstairs then. I'll be. Give me 1 second. All right. How about now? Is it better?
Okay, that's better. Thank you.
That's better. Give me 1 second. I'm not gonna be able to see. Okay. All right. So. All right. So where were we? So we were here, right? This is kind of like the contents of.
Sorry, you should share your screen first because
Oh, it's not
you
sharing.
stop, you stop sharing.
It was. Oh, gotcha. Okay. I'm so sorry. I am. It's because I'm downstairs and there are no second screen here. Can you see my screen?
Yes, but
You can
yeah,
see.
yeah,
You can see
yeah,
your
yeah,
face.
yeah, yeah.
Okay. Cool. So just we're gonna move to part one here. Just really. Oh yeah. Okay. My references. I'm using references. This is like the material today is I use I like from several there are two books that I've been using a lot. This is the first one. This is where most of the first one, the from the renewable and efficient electric power systems from by Wiley publisher. That's mostly of the fundamental of like the electrical theory of that. And then the second one, which is like I found the picture. It's large scale solar power system, right? So this is just like giving you the idea on how to build, how to design, and what the kind of like the process behind when you're about when you're going to have a project of like large scale utility connected system. So somehow when you're finally graduate, right, you're finally graduating, and then you go into the job market, at least you kind of like have the idea on how you build the solar system, because somehow in Indonesia I think there are there are still a lot of opportunities there to for solar engineers, I would say. So this is just kind of like the idea or what my references and plus Google or AI. Okay. All right. So the part one, uh, the material itself. I'm not gonna go too deep in here. Okay. So I will just read out loud here first. So solar resource, we know that, or sunlight, right? It has like electromagnetic radiation emitted by the sun, and then it will use to generate the electricity, right? Or heat thermal in general, like if you're talking, I think one of the material is about solar thermal, so that's one item from sun that can be converted into energy. And then the next one is like technologies utilizing the resource, right? There are two most common one, like photovoltaics, which is like it convert excuse me which is it converts the sunlight directly into the electricity using the semiconductor materials, right? Primarily silicon, right? And then the other one is concentrating solar power or CSP. This is using mirrors to concentrate sunlight, typically used for large scale power plants. I see this a lot. It's not so, at least in the US, what I've seen a lot, like CSP, I saw that a lot in Nevada. Um, in Nevada is like if you heard Las Vegas, so that's where like the Nevada, Las Vegas is the city of one of the city, the biggest city, in Nevada, and that's where I saw a lot of this CSP. Like if you pass by the highway, then you just like, because it's very dry over there. It's very flat, dry, sandy, desert, desert, no, desert. It's not dessert. Dessert is like what you eat after desert. It's a desert environment, so it's very hot in there, it's very dry, you barely see get rain, okay, rainfall over there. So it's just like they have like a very big of this CSP, like thermal solar thermal power plants over there. But like photovoltaics itself, I see a lot of that um in Arizona, I know that, and then as well as in New Mexico. So it's like closer to it's on the south side of it's kind of like similar, but it's uh I think it's, I don't know why, more in Nevada and less than in Arizona, but they are mostly photovoltaics. You would see a lot of in New Mexico. It's like on the borderline between uh, America and Mexico. That's where a lot of you see this solar PV, the photovoltaics. Um, and then so that one, and then, well, the common material for the solar PV is silicon. When I was doing my internship, we do mostly the projects or like research at that time was using the silicon based. There was one project about thin film at that time, so it's just a different material, right? So tin silicon, I will explain more later when we go to the manufacturing. But it's like the silicon is just usually it comes from an ingot and then it's like this size. But then the thin film, it's like usually like a bigger, like a most like a paper plastic paper. So it's like this is like a big paper, and then there's that thin film. At that time when I was doing my internship there, there was a there was a research going on at that time, was for the MIT, the you may heard the MIT, Massachusetts Institute of Technology. They had a at that time they had research and on how to use the thin film on a car. So they use the rooftop of a car, and then they use the thin film to produce the electricity for the car at that time. Because thin film, like silicon, is very it's very if you see silicon is like this, they're like very fragile, like you cannot bend it, you can it breaks, it's like it breaks, it breaks, it's scattered, you know. That's what silicon is. But the thin film, since it's like a paper piece of paper, thin, very thin, and then it's more flexible. So that's why that's just several material used there. They have pros and cons, but I think this was explained before. I just give you the idea on how I saw it right at that time. So that's just like the material component. Support materials is usually like for the silicon. Maybe there's for film, but what I saw with thin film is it's more like they don't really have it framed, like it didn't use any glass casing or metal frames or anti-reflective coatings, things like that, right? Okay, so that, and then next, okay, so this is the manufacturing. um like I will read this real quick. Solar manufacturing encompasses the production of products and materials across the solar value chain, right? um Related to PV. Those systems are comprised of PV modules, racking and wiring, power electronics, and system monitoring devices, all of which are manufactured. So this is how the silicon itself, the PV cell, and then and then becoming model. So it comes from this polysilicon, right, material, and then it's kind of like sand, you know, and then they do they produce the ingot. It's called the ingot. So imagine, I think the way I see this, imagine like it's gold when you're like get it from mining, the gold mining, and then you burn it and then it becomes solid. So that's what ingot is. It's just literally the polysilicon material, and then it becomes a solid, right? And then from these they cut it precisely, like using the diamond saw. So they cut it like very very thin, and then it becomes the wafer, and then the cell, like they do something with the wafer, the process itself, and then it becomes the cell, where now it has the p and n junction, right, which is like it's the semiconductor, right? And then from the cell itself they arrange it series and parallel, and then they put material frames, and then they laminate it inside the, it's like an oven, and then now it becomes the module, right? And then from module, you combine several modules and then put the racking into an area, specific area, and then you put mounting itself, and then now it becomes a system, right? So that's just how it is, right? The from the very very the material level into the system level, right? And then in further is to convert from the DC output of the project into the AC, so then it can be delivered to the power grid, and then eventually it's going to go to the customer. And then next, so this is how, right? This is, we see the large ingot, and then from ingot it's cut, and then it's being sliced and then clean, right? And then this is the wafer, and then they put like N and P junction, and then it becomes the solar cell, right? One each individual solar cell, and then they put the wiring, right? They put the wiring, they combine the P and N, and then now it becomes, it's connecting, like it has the positive output, the P output, and then the N output. And then they put it in a, so if we, I will have it here for this one specifically. I will jump into here first. So if we do see here, this is how the model, it's it's developed, right? So this is the junction box, which is like, it has the output P and N output of that, right? And then this is the backseat. The backseat usually kind of like a wood type of material, so it's sturdy. It's like, kalau kayak foto album kan ada yang lapisan itunya di belakang, triplexnya ya. Nah, it's like that. Backsheet is like that. It's essentially like that. And then this is what it's called encapsulant, right? Encapsulant, or it's also short from EVA. So EVA, encapsulant, is like, I will say it in Indonesia. So ini jadi kayak, encapsulant itu kayak dia,
Laminating bukan ya?
No, it's not the laminating. Itu kayak paper, ya. Dia tuh material kayak sedikit campuran antara, dia bentuknya tuh pokoknya kayak paper gitu, kayak paper, apa sih bahasa Indonesia? Apa bahasa
Kertas.
Indonesia? Kertas ya. Kayak kertas, tapi dia ada kayak, ada polimernya dikit. Jadi kalau dia dipanaskan, dia jadi, meleleh. Tapi melelehnya itu dia, jadi dia itu kayak absorber. Jadi untuk, kalau fungsinya itu encapsulant, jadi ada dua encapsulant sini di bawah ya, sebelum the backsheet, sama the solar cell-nya, sama encapsulant lagi kan. Jadi dia tuh benar-benar kayak shock absorber. So it's just, kind of like untuk protection, supaya dia kayak lem, tapi dia jadi pada saat dipanaskan, dia tuh kayak menempel sama si selnya itu. Jadi selnya itu dia stay stay in place, doesn't move, it doesn't, so, protection, it's for protection, tapi dia meleleh. Nah, kalau yang di atas ini pada saat dia dipanaskan, itu dia kayak blanket the solar cell, right? So dia melindungi. Jadi encapsulant itu dari belakang, dari bawahnya si solar, karena dia kan sangat fragile tuh, sangat, gampang banget, dia rapuh banget, itu gampang banget pecah di ini dikit, pecah dia. Nah, itu jadi fungsinya encapsulant itu, dia itu memprotek di bawah dan di atasnya gitu. Bener-bener dia memprotek sininya, dia transparan kan, dia transparan. So it doesn't affect any light that comes to it. So that's just pretty much the encapsulant. And then this is where the solar cell, where you already wiring all the P and N junction of it. And then you got the tempered glass. Tempered meaning, you know what it means, right? It's strengthened, like, dia bukan gelas biasa yang gampang pecah. Dia ada material yang bikin dia tuh jauh lebih kuat dibandingkan gelas yang biasa. Makanya dia sebut tempered glass, right? It's not regular glass. And then there's the aluminum frame, right, on this side, to keep everything in one place. So once it gets to there, and this is the process. And then, pada saat dia udah, when you already layer them, right, and then you put them in a laminate, in an oven. Essentially, it's a big oven. When I was working for Fraunhofer, it's a laboratory, right? It's a laboratory because it's an R&D, research and development. So there was a big oven, and then you put this, the one that you already layered them, and then you put the, frame, you put them inside, and then it will be heated for how many, I think like it was like 30 minutes. And then when it comes out, it's just like essentially not like already a complete module. It becomes like, like this already this, but it has to be put inside the oven to make them like glued together. So that's what this one is right now, that they are already becoming the module. This has become a module, and then you combine them, and then put the supporting, and now it becomes the system, right? So there's the bus bar. The bus bar is like where all the and then this is the bus bar, and then this is the fingers, right? So, and then this one I already said that. Oh, this is okay. So this is the encapsulant. It's a material such as epoxy or silicone or polyurethane used to coat fill, right? So to coat and then to fill, right? To fill is like if any gaps, it will fill. And then enclose components, particularly electronics, to provide protection against. Okay, so it's a protection against environmental hazard like moisture. So moisture, dust, and shock. So untuk kelembaban, dia menjaga kelembaban karena dia menempel seluruh permukaan depan dan belakang, jadi tidak ada moisture yang masuk, tidak ada uap-uap air yang masuk, because moisture is not good for electronic for panel in general, for like silicon. There's one thing called degradation. So degradation is like what is it in degradation? It's like penurunan kualitas, penurunan degradation is a degraded penurunan, not just quality but also like the electrical output of the panel itself. So you want to make sure no moisture get into the panel, and then dust as well, because when dust gets into the panel, what happens is like it makes it less sunlight gets into the cell itself, so the production gets lower. So that's why, like, typically, and shock is like, when it's moving somehow during the transportation or during the construction, when there's a shock, want to make sure that it doesn't break the cell, because when the cell is broken, and then it's almost, it's degradation, slower the output of it. So you just want to make sure of this. And also one thing, I remember watching, I don't know, kalian sudah nonton film apa tuh, drama apa tuh yang si Shine on Me ya, Shine on Me, when that talks about the solar company, and then one time it was snowing, and then snow got into the frame, into the surface, and then they were all cleaning it, right? So that's one thing, that if you, as soon as and especially if it's snowing, right? Snow is a different thing, it's just like, if you leave it, it's gonna get hard, and when it hard, it's just like stays, it can break the glass pretty much. So it's just something like, it depends on where you have your solar PV project. You just like, all of these are like maintenance. If it rains a lot, like moisture can get into the, how do you handle that? If it's in the desert where it's very sand, a lot of sand over there, like a lot of dust, how you maintain to clean, right? So things like that. So what else? This one, effective. Okay, that's fine. And then what's this? I'll let you go into this. This is just, you can read it. I leave it here. Ingot and wafer, the cell fabrication. We talk about that, the module assembly. We talk about that somehow. Thin film, we talk about it a little bit. It's just different material. And I think application really also like different ish. So that's part one. I'm gonna pause here before I jump into part two. Any concern? Any question? Or how do we handle this, Maya? Should we just keep the question at the very end, or
It's up
what's
to
the
you.
approach?
Can keep it at the last session. Or maybe if anyone wants to ask a questions, they can ask right away.
Okay, I'm gonna pause here. If any question, I will limit the question just to, if any. I cannot see you. If you raise your hand, I cannot see you. So you
I will
should.
tell you if any
Okay, cool.
students raise their hands. Any question, guys? So far, so good. I think
Think
they're
we're
so
good.
yeah, they're good.
Okay. Okay. Next is part two. This is where we talk about the solar. This is the science behind. So how eventually what's the solar? No, this is more of like the sun and the earth relation in relation to the solar production itself. That's just the bottom line or the highlight. All right. So next, I will have a lot of pictures here because I like talk more with the picture. I think it makes more sense to me if I see. So this is just one. So the solar, as we know, sun, it moves a lot, right? Well, it's not sun is not moving. It was Earth orbiting the sun, but because of that movement, it causes. But during the day, like in regular day, right? What we see, if I have, if, for example, this is my house and I have the solar installed on my rooftop, right? For example, I will see the movement like from morning, like the sun rises from east, and then once it's the at noon time, like in if it's in Indonesia, like around 12, it's gonna be right on top of me, and then soon it's shift towards the west, right? And then it's gonna be sunset. So at least from us, from if I have a house like this, I will see the production. Like if I have solar panel here, I will see the difference production or like electricity, produced by this panel on my rooftop differently from each day, right? Like not from each day, during the hours, right? From 6 a.m., for example, from the sunrise to the 6 p.m. That's if you live in Indonesia. But if you live in the US like me, it's totally different. It changes depending on the season. So that's what the relation of all of those, like where do you live? If I live in Indonesia versus if I live in Pennsylvania right now, if I have solar PV on my rooftop, what would be the different production? So that's kind of like the idea of this, right? Where you are on Earth, it determines where your solar production is. But how to calculate that, how to correlate all of those, like this is what this is what it is, like the solar resource. This is what it's all about, right? So um there are there are so many terms here, there are so many formulas here, but I'm not gonna go into deep. If you somehow finally take your master or your doctor PhD, and then you can go details of all those formulas. I'm not going to bring it up here. This is just kind of like an introduction of that, right? So there is so if this is your panel, and this is the sun, the you have to keep in mind that the solar that touch the panel itself, anything that perpendicular, right? Yang tegak lurus, sinar yang tegak lurus, that's the strongest, that's the highest electricity produced by the panel itself. So how you design like it depends on where your location on earth. You can be in Indonesia, you can be in the US, you can be in Australia, you can be in Europe, right? So depending on where your location, you want to make sure your panel, when you design it, you get the sunlight that perpendicular to the surface of the glass, right? Or to the cell itself. You want that one. So, but because earth rotates around the sun, there are changes, there are shifts. It shifts around, right? So this is for next is just like this. So okay, this is where the time of the day, right? From if you see the solar panel, when it's sunrise, it's zero. When it's dark, when there are no sun light touching the cell, you will not get any energy, right? Any electricity produced, nothing. But as soon as it sun rises and then start getting sun, you will see that it starts increasing, right? And then as the sun is already perpendicular to your head, and then your panel kind of like get to the max, that's where your energy production is kind of like the highest. And then as it gets to the afternoon, it gets lower and lower and lower, and to the point when it's sunset, you get zero kilowatt hour, produced. So during the night, you don't get anything, right? So that's this, which is similar to this one, right? Similar to this one. But then now you're getting more of. All right, I like to explain this one more. Oh, in this is so if you are in Indonesia, which is we're kind of like in the equatorial, right? The the rule of thumb, right? The rule of thumb, bahasa Indonesia rule of thumb apa sih Maya? Tahu nggak?
Apa ya?
Rule of thumb itu biasanya apa ya kalau bahasa Indonesia rule of thumb, aturan paling gampangnya lah ini bahasanya, kalau mungkin di Indonesia kan kayak gitu lah, aturan paling 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 gampang lah untuk diikuti gitu ya. Kalau kita di Indonesia kan dia zero ya, secara utara dan selatan itu kan dia 6 derajat utara terus 24 derajat selatan ya kalau nggak salah ya, kita tuh berada di equatorial line kan. Jadi sepanjang tahun itu kalau kita lihat matahari kita berrotasi mengelilingi, kita berrotasi setiap hari dan kita mengelilingi matahari dalam setahun, ya. Itu secara garis besar matahari itu bakal di daerah ekuator itu masih akan bakal sama setiap tahunnya. Jumlah energi yang bakal kita dapatkan di panel kita itu at least uniform from time to time in 1 year, every day, kind of like similar, right? Dan rule of thumb-nya, kalau kita pasang panel surya di daerah ekuator itu sebenarnya kalau mau perpendicular tegak lurus itu kan kita nol ya, kita flat aja lurus horizontal kayak gini panel kita. Tapi kita harus mempertimbangkan bahwa ada faktor hujan. Tadi kan kita udah bilang kita nggak mau tuh moisture itu masuk ke dalam modul kita atau panel kita kan. So the rule of thumb, right? Paling gampangnya lah, we have to tilt it like 10 degrees. So what is this 10 degrees does to your module? It to ensure when it rains, it flows down. So even though we are in an equatorial line, it's not exactly we're gonna put our module like 0%. We have to tilt it a little bit, 10 degrees to the horizontal, and then to make sure the water flows down so it doesn't get, the moisture doesn't get into the module itself. So that's the rule of thumb. But what if you're not in Indonesia, right? You are not within the equatorial line. So ini contohnya kayak di Amerika, ya kayak misalkan di sinilah ya di Pennsylvania. Jadi kalau kita lihat sini, if you see here, right, this is long night, short day, and then this is long day, short night, right? Nah, ini kalau di Amerika itu mungkin gambarnya paling jelas namanya. Ini kalau di Amerika short day itu long night itu berarti dia winter. Itu lagi winter. Kalau musim dingin di sini itu siang harinya itu pendek. Yang pasti kurang dari 12 jam, bisa 8 jam, bisa 9 jam. Dia kurang, tapi naik malamnya itu jadi lebih panjang. Nah, kenapa, apa yang terjadi pada saat ini? Jadi pada saat ini kalau kita lihat itu, ini daerah utara. Kalau daerah yang di utara itu kan dia ada tilted ya 23 derajat ini kalau kita lihat bumi terhadap sun itu berputar, dia ada tilted 23 derajat itu. Nah, pada saat winter, matahari itu lebih banyak ke daerah selatan. Makanya kalau di Australia, kalau kita di sini winter, daerah Australia itu dia summer. Karena di situ pada saat itu dia panas-panasnya karena dia tiltednya segini, jadi ke arah sini itu matahari panas-panasnya. Tapi kalau ke arah utara, ini di selatan nih, ini ke arah utara lebih dikit mataharinya. Nah, ini makanya pada saat winter itu in relationnya dengan solar PV production itu kita bisa expect bahwa during winter time your solar PV production will be less. So that's what it is, right? And then if you have to use your backup, for example, like storage, and then go for it, right? So that's during the winter. And how about during the summer? So this is winter, and then through the summer, this is where spring is. So in between winter and summer is spring, musim semi. Kayak sekarang ini musim semi. Musim semi itu, musim semi and this is musim fall or autumn ya. It's the same. Kalau Amerika menyebutnya fall season. Tapi kalau Europe kayaknya dia pakai autumn. But it's the same thing. So spring and autumn, the night and daytime, they are similar, like 12 hours each. But winter and summer is totally different. During summer, so when this is like tilted like this, and then during summer at the northern hemisphere, that's where like it's very hot and it's very long day. So biasanya itu subuh itu sunrise itu jam 4 itu udah sunrise. Terus terbenamnya matahari itu jam 9 malam. Jadi kalau pas musim summer itu orang pada nangis semua, itu panjang banget itu waktunya untuk puasa. So that's just how to the idea. But then at the same time when it's summer here, right? It's winter here on the southern part. So at the summertime, we will see the solar PV production will be like much increasing because it's just like a long hours, you know. So that's how the correlation of that, right? Just give you the idea on like what the expectation of like solar PV production. Well, if it's in Indonesia, you would expect like every month is the same or similar. But in when you're northern hemisphere or like southern hemisphere, you would not see the same throughout the years, throughout the month, kind of. So that's just the idea of this. And then there are key aspects of solar resource like irradiance. Irradiance is like direct beam. So when I said the perpendicular direct perpendicular to the cell, that's the direct beam. And then diffuse, for example, like if there are cloud, right? If there are cloud, and then the sun touch the cloud, and then it's scattered. So if it's clear day, and then yeah, all becomes a direct beam. If there are no cloud, you know. But then if somehow it's a cloudy day, and then the sun touch the cloud, and then from the cloud goes to your um module, right, to panel, it's different energy, if it's direct and then diffuse. And then global is kind of like the radiation, for example, like if somehow there's a building, and then the sun gets to the building and then gets to the panel, that's a kind of like a different 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 irradiance. So that, and then what is this? Oh, resource variability. So the intensity of the resource varies based on latitude. Of course, latitude is like, you're up north or like south. Time of the day, yeah, it's obvious. Season, like, just as say winter and versus summer. Atmospheric condition like cloud cover and pollution. Pollution. So kayak kalau kayak London ya, kayaknya London itu kan dia sering cloudy gitu kan, dia sering cloudy and rain. Kalau kamu bangun solar rooftop di London, nggak bakal sebanyak energi yang dihasilkan, itu nggak bakal sebanyak kamu di kayak misalkan di sini di Pennsylvania. Pennsylvania itu sunny, nggak ada, jarang ada hujan, tapi nggak kayak, nggak, dia kalau terang jarang, nggak banyak awan gitu loh, not cloudy. Terus so direct direct beam, sunbeam, right? And then what else? Pollution. Sorry, di sini nggak ada polusi. Nggak kayak di Jakarta kayaknya ya. Kalau di Jakarta itu kalau kelihatan banget itu, kita baru terbang mau mendarat aja tuh, tebal banget itu polusi. So you would expect, if you really would like to build your solar PV project, right? You have to consider all of these. This this impacts your solar production, right? Okay, what else? Next. Maya, until what time? How long is what time is my limit here?
100 minutes, 1 hour,
So
40 minutes.
So 9, 15, 10, 15 is like 60, and then another 40 minutes?
Yeah.
Okay, cool. I just want to make sure. All right, so we're going to be like 10, 15 plus 40. It's almost 11. Cool. That just, hopefully nobody's falling asleep here. All right, so next. All right, so this is just a sample that I took from the PVC's result, but this is just to show you how all those solar resources, right? Solar, how does that impact your production? So this is, for example, like this is in Geneva, Switzerland, right? So for example, this is, you will see this back when we're having the PVCs simulation. So you will see, for example, here, this is in Switzerland location. The data for the weather data, it comes from the metronome. That's one of the weather statistical data acquired, right? So this says like if you're in Switzerland throughout the month, throughout the year, you will see here in January your production is around, so this is the global, it's a global horizontal irradiation, and then horizontal diffuse. So this is the direct beam, and then this is the diffuse irradiation. So you will see here during the January, February, Switzerland is in northern hemisphere. Like if you see January, winter is essentially pretty much from I think like September, November, October. No, actually December. Sometimes like in December, January, February, that's where kind of like winter time. So if you see here the direct, right, the direct and diffuse, they are very small. But then March starting to get up because that's where it starts the spring. Spring starts like March, April, May. 3 months, right? Every 3 months. So then, and then you see during uh the springtime, right? This is it, it's higher than the winter, right? And then now we get to June. June is summer. June, July, August, that's like summer time. That's where you see like the highest production here. Like if you see like June 193 and then July is 196, right? So that's July is the peak of summer. That's the highest production, right? And then August it get less, but still more. But then September comes. September is when it starts the fall or autumn season, right? And then get less and less. And we get to November and December where that's the winter. And you will see this much less than the summer and or the fall, right? So that's just to give you the idea that that's how it is. That's in northern hemisphere. If you see Australia, for example, it will be the opposite, right? It will be the opposite. If you see January is the lowest, you will see in Australia will be higher, much, much higher. So it's just like kind of like give you the idea that it does have the impact, all this solar rotation and then solar what is it? What is it after rotation? When rotation is like every day. Revolution? Is that what it's called like throughout the year? What is it called?
Revolution?
Yeah, what is it called? So every day is like rotation. We rotate every day. But then throughout the year, what is it called? Is it
Rot-
revolution? No.
I don't
What is
know.
it?
Rotate through the earth, through the sun.
I forgot what is it called.
It's revolution. I thought it's revolution.
Huh? What is it?
It's
Revolution?
revolution. Yeah,
Maybe.
maybe.
If anyone know, please remind us. It's high school. Oh, it's a long time ago. All right. Anyway, so that's the end of part 2. I'm gonna pause here before we get to the large scale solar power system design. Any questions?
Any question, guys? Don't you wonder how US cover their um solar system during the winter?
Good question. All right. I think that's it. Let's just move on. It's 10:23, so kind of like have like 20 minutes. Um, all right. Next. This is my most favorite part of it. It's like you can tell me all this theory. I'm a very hands-on. Jadi kalau misalkan lebih kalau teori tuh whatever gitu loh. Tapi kalau bagian prakteknya itu yang lebih it's easier for me to understand when I get to the hands-on experience or like practical knowledge. That's what I like the most, and that's why I am here now. So anyway, right, this is the design. When you designing the system, um, what what the considerations are. Okay, so let's see here. All right, this is I took from Google. So large scale solar system, right? Design. So large scale, let me just read this real quick and then we'll get to, where all this simulation. All right, large scale solar system design involves utility scale photovoltaic. So utility um, is utilities like in PLN, right? PLN. So utility scale photovoltaic PV projects that produce massive amounts of electricity for the grid, usually requiring 5 to 7 acres per megawatt. So in the US, they use a lot of like no, not the SI standard international, no. So acre itu kalau dalam bahasa kita hektar. Nah, kalau standar internasional kan dia meter squares. Jadi kalau di US, they usually say acres per megawatt, right? How many acres? 5 to 7 hektar per megawatt. Jadi untuk menghasilkan 1 megawatt itu dibutuhkan tanah 5 sampai 7 tergantung lokasinya di mana. Karena lokasinya ya semua yang kita jelaskan tadi, masalah solar resource-nya. Nah, kalau di Indonesia kita pakai sistem kilowatt per meter square. Jadi berapa meter modul lahannya itu untuk menghasilkan 1 kilowatt, for example, or like megawatt for meter square. Okay, so then next is like key design aspect, focus on site planning, high efficiency, the panels, right? The single axis tracking system, or like central or string inverters to optimize energy yields, right? And then this is just key design components. It's already mentioned, but this is explained, elaborated more. Site planning and layout, right? Requires large contiguous areas, typically 20-30 feet for O&M access paths, and 20-50 setbacks. So lahan kalau kita membangun solar project ya, itu harus ada. Jadi kita misalkan, coba contoh gambar ini, coba boleh lihat, ada nggak contoh gambar? Oke, kita coba lihat di sini ya. Nah ini kan kita lihat nih, ini panelnya ya, panelnya satu string itu antara string yang satu dengan string yang lain itu harus ada jarak. Nah ini yang tadi dibilang di sini, this is 20-30 feet for O&M access. So kita butuh space antara string yang satu dengan string yang lain itu untuk O&M. Jadi kalau misalkan kayak kita harus membersihkan si modul ini karena dia banyak dustnya, debunya, ya kan kita lewat sini nih. Nah itu yang dibilang tadi. Terus kalau setbacks, 20-50 feet setbacks itu lebih ke ininya, kalau kita ada pagarnya gitu, itu antara dari ujung sini ke pagar itu sekitar segitu. Jadi kenapa? Karena sometimes kita butuh truk misalkan masuk untuk ke dalam lahan atau mobil masuk ke, misalkan dia gede banget gitu ya, nggak bisa tuh, susah tuh kalau mau jalan, atau kalau misalkan kita mau ada maintenance apa, mobilnya butuh jalan masuk. Nah itu dia jarak dari sini ke pagar itu sekitar berapa itu dijelaskan di sini. 20-50 setbacks, right? Jadi kalau ada mobil mau masuk atau lewat dia bisa gitu lah. Itu satu. Terus what is this? Layout design often involves using software. Okay, yeah. So PVKs, Unreal, SAM to define row spacing. Okay. Minimizing shading and maximizing land use, right? Jadi ada namanya shading. Shading itu shadow apa sih, bayangan ya? Bayangan shading. Shading itu jadi bayangan. Misalkan nih, di sini boleh nggak di tengah sini ada pohon tinggi? Apa ngaruhnya kalau misalkan ada pohon tinggi? Atau jangan di situ, di samping pagar sini nih. Atau misalkan dia nih di tengah hutan nih, banyak pohon di sekitarannya. Apa yang akan terjadi gitu? Ada yang namanya shading. Shading itu apa sih? Shading itu bayangan yang kena ke modul ini ya, terus jadinya dia kurang hasil electricity-nya yang energi yang di-generate. Nah, susahnya kalau fotovoltaik itu kayak gini. Kalau yang susahnya modul panel kayak gini, itu susahnya gini. Kalau misalkan ada shading di satu sel ini akan ada berapa nih? 5 kali 3, 6, 8, 5 kali 8, 40 sel berarti kan ya dalam satu modul nih, satu panel. Ada 40 sel. Misalkan ada satu sel yang kena shading, kena bayangan gitu, ini 0 keluarannya. Jadi kalau solar project itu sangat penting untuk shading itu sebisa mungkin nggak ada gitu. Ya, itu yang nanti kita mungkin ada kali di bawah. Kalau enggak nanti ada di PVC tutorialnya. Itu nanti kalian bisa baca apa sih efeknya shading itu terhadap hasil electricity-nya yang di-produce. Right? Nah itu satu. Terus apa lagi nih dibilangnya? So and then mounting and tracking, right? Mounting is ini supportnya nih. Ini mounting. Terus tracking itu apa? Tracking itu dia motor yang bisa menggerakkan panel itu mengikuti arah sinar matahari, so tracking gitu. Kalau yang ini fix dia nggak ada trackingnya, dia fix still gitu, fix panel. Jadi nggak bergerak mengikuti matahari gitu. Kalau misalkan lagi dari pagi dia munculnya dari timur datang ke sini terus naik matahari bergerak sini dia juga ikutan bergerak sampai ke sana gitu loh ya, sampai terbenam. Jadi itu dia memaksimalkan perpendicular yang tegak lurus, sinar matahari yang tegak lurus ke panel itu. Nah, tapi kalau enggak dia tetap seperti itu namanya fix gitu. Nah, jadi itu satu ininya ya, satu key design component and consideration. Apa sih bedanya nanti? Apa sih bedanya mountingnya itu kalau saya pakai tracking sama fix? It's all about the money. Harganya beda, jauh banget bedanya. Kalau pakai tracking itu karena dia motor ya, ada motor. Itu motor kalau udah itu harganya jauh lebih mahal dibanding fix. Nah, terus electrical design, modern projects frequently adopt virtual center design, utilizing DC string inverters clustered at equipment paths to reduce rather than manage costly AC losses. Well, ini technology inverter. It depends on, it's most likely. And then grid integration. The design must account for substation design, transformer placement, and local grid connection codes. Ini kalau di US masih itu kan tadi yang saya bilang backgroundnya ya bahwa di US itu kan dia utility company itu dia private ya, milik swasta. Nah, tapi ada banyak, misalkan di Massachusetts itu ada satu perusahaan, terus kalau di New York itu kayak di New York ada 2 perusahaan besar, yang salah satu yang PSEG Long Island di mana saya dulu pernah kerja, transmission planning, terus ada satu yang daerah Manhattan itu dia Con Edison. Dia jadi daerah Manhattan itu kan daerah pusat ya, kayak misalkan kalau kita Jakarta itu, nah Con Edison itu mengcover itu. Nah, tiap utility company ini itu punya code yang berbeda-beda. Mereka punya kriteria yang berbeda-beda. Ada yang mirip, sebagian besar dia sama, tapi ada hal-hal tertentu misalkan kalau dia di Manhattan itu kan beda ya, dia lebih ke underground, terus karena dia sudah sangat padat banget, sangat condensed gitu, jadi dia punya persyaratan requirement itu yang very very strict, very very stringent, comparing with other area where it's just like mostly like household So that's just like something take into consideration. That's why it says here grid integration. You should take consideration of the local grid connection codes. So, and then optimization. Okay, and then popular approaches, fixed tilt versus trackers. We explained it. We're gonna explain more. Virtual centralized and centralized. Well, not really sure what it is, virtual centralized, but it is what it is. And then there's regulatory and physical constraint. Regulatory lebih ke waktu saya di PLN itu ada banyak, sering mereka keluarkan peraturan menteri nomor sekian. Misalkan dia peraturan menteri nomor sekian itu terkait dengan subsidinya si solar gitu loh. Tapi itu bisa berubah-berubah. Jadi salah satu hal yang juga harus di take into consideration, ya, hal-hal yang harus diperhatikan, harus harus dipertimbangkan itu regulatory aspect as well. So that, and then topography and land, and then environmental impact as well, right? That's just where were we? Okay. Ranking system. I'll explain more. Power electronics, inverters. And then let's go to the simulation of grid connected system. I briefly mentioned about this one. So this is what I used a long time ago. Well, when I was at my school, when I was during my study, I was using the PVSys software simulation. So this is just one out of several, right? It mentions here there is, what is that software? Oh, for example, PV case. That's another software. There's NREL. NREL is National Renewable Energy Laboratory in the U.S. It's very famous in the U.S. It's called SAM. I forget what this SAM means, but it's just one of SAM. It's one of the software. And then so PVSys is a comprehensive software